Now, what are some useful properties that we can take advantage of when we look at contour diagrams or study contour diagrams? One of the important assumptions that we're almost universally going to use is that the Z values in a contour diagram are evenly spaced. They're going to be labeled with numbers that change linearly or are evenly spaced in Z. We're not going to see things where it's 10, then 2, then 1. Then interpreting the contour diagram gets a lot more challenging. So we're not going to do that. If the contours we're presented with or that we build ourselves are evenly spaced in their Z values, then we have that property that we examined earlier, that contour lines that are closer together mean a more rapid change when we change our position X and Y, or steeper slopes on the path or on the surface. If they're further apart, you get the opposite. It means a flatter region, less aggressively steep. And it's also worth noting that peaks and valleys actually look identical on a contour diagram unless we have the values associated with it. For example, let's do 3 contours here. I give you 3 contours and you can't tell what those are. You can't tell whether these are coming out of the page or in towards the page until we label it. If we label that 2, 4, 6, then we know that there's a peak somewhere in the middle here. If we labeled it 2, 4, 6 going this way, then we're going down, and this would be a valley at the center of this set of contours. So without seeing the labels, we can't really tell much about the shape of the surface, but with the labels, we can tell quite a bit about how quickly the surface is coming out towards us or into the page, as in this case. And it's surprisingly informative we can do a pretty good visualization in our minds of what the surface looks like based only on a contour diagram. Let's take a look at an example here. And this is a subtle one. It's worth exploring in detail here. So we're going to do a study of contours or level sets. Again, those are synonyms. And, pardon me, try to make this as accurate as possible for our first one. There we go. So our function is x plus y all squared defines some kind of surface. So again, we're going to apply that this is a Z value. And a contour diagram is a set of x and y curves because the Z is going to be coming from the label of each contour. So where do we start? Well, in a question on an exam or in a test, we'll give you some Z values to use, so we all start with the same goals. In practice, you'd have to pick some representative values based on what you know about the function. Let's start off here with a nice simple value like 1. So what we're doing is letting Z equal 1 and then asking which x and y values give that Z value. Again, different x and y values run through this function will give us different z's. What are the ones that give us the exact value 1 as the output? Well, all we do is set 1 equal to our function, or 1 is equal to x plus y all squared. Okay, now the first question you ask yourself is, can we sketch that curve, that shape, whatever it is? X plus y all squared equals 1. It would help to simplify. I certainly don't know what that looks like just glancing at it, and I'm probably going to make a silly mistake if I assume it's something like a quadratic, because it's not quite classic quadratic stuff. So we're going to simplify that first. X plus y all squared equals 1. Well, let's take a square root of both sides. And if that's the case, we're going to end up with x plus y on the left. On the right, we could end up with 2 roots, 1 or negative 1. And that leads to 2 curves. Y could be equal to 1 minus x, or y equals, well, negative 1, bring the negative x over, negative 1, negative x. Both lead to z equals 1 values. Any point along those two lines will give us z equals 1. So let's put some labels on here. 1, 2, 1, 2. And what do these curves look like? Well, this is y equals intercept 1, slope negative 1. Intercept 1, slope negative 1. Let's do that again and again. There we go. And likewise, down here at negative 1. There we go. Both of those, I'll do it in green here, would be caught with the Z label. So Z values are in green. The Z label 1. All the points here, if I plugged any one of those points into the function, we would get a resulting Z value of exactly 1. All right, so what else can we do with this? Well, we've just started. This is our first example. We've just done all this work, and we have 1 Z values contours. Turns out to be 2 separate curves, that's fine, but we only looked at 1 value. Let's do this next thing. Let's say let Z equal 2. Then 2 is equal to x plus y squared. So we have root 2, or negative root 2, equals x plus y. And so we get 2 curves again. Y equals root 2, bring the x over, root 2 minus x, or y equals negative root 2 minus x. Well, negative root 2 is about 1.4, or negative 1.4. That's 1.5. 1.4 is about there. 1.4 is a little bit below there. And we put those onto our contour diagram. Let me try to do that. Hope it straightens out. There we go. Perfect. 1.4, about more than halfway. There we go. Both of those contours in green would get the Z value 2. And I think we start seeing a pattern. Hey, if I had a 3 in here, I would get root 3 and root 3. And if I had a 4, I would get root 4 and root 4. So we start to see the pattern. The root 4 is the easiest one, of course, because it's just 2. In terms of its x and y values, but it corresponds to z equals 4. So 4 and 4 down here. And in between those last two I just drew is going to be our 3. Somewhere in here. There we go. So 3, 1, 2, 3, 4, 1, 2, 3, 4. So it's not a trivial contour diagram by any stretch of the imagination. We could even go one step further. We could actually do it at 0 as well, and we'd find, not that horrible sloppy line I just drew there, we would find, wow, it does not like that. One last try. Do that. There we go. And that would be height 0. I give up. So that would be the contour diagram for a number of representative heights, Z values, over the shape. What does this look like? Okay, we have the contour diagram now, and we've seen how that calculation is performed. But what are we actually defining as a surface here? Well, let's take a look back. We have a height 0, height 1, 2, 3, 4. So as we move this way, we're coming out of the page. As we move this way, we're also coming out of the page. And a couple of other things, it's fairly flat in this region here, and then it gets steeper as we move outwards. So what is that going to look like? Well, I think if we look down this way, because we see all these parallel lines, we're going to see the same thing if we look in from this edge here. So if we view this way, what are we going to see? Well, we're going to see, in the Z direction here, we're going to see a height 0, and then a height 1, and then a height 4, and a 3, and a 2. 1, 2, 3, 4. We're going to see something that looks like a parabola, flat and then steeper. So that squared term, this is where it's playing its role in terms of the shape of the surface we're obtaining. And the way I would describe this is as a parabolic trough. because it's straight. It's like a piece of trough that you see in a barn or that you see on the side of a house to carry water. It's one long repeated structure straight back out of the page at us here. It's just aligned not with the axes, but it's aligned this way. The bottom of the trough is here, and the sides of the trough move up and up as you move towards the northeast or southwest in this particular diagram. So we can get some interesting shapes, and we can get to the idea of the surface behind those shapes by taking our function and picking representative z values and seeing what level curves we obtain or what contours we obtain. All right, well, one isn't enough practice. Let's do two. And just notice slight difference from the last one. The last example was x plus y all squared. Here it's x squared plus y squared. Notice those are not the same things at all. Why not? Because we'd expand this. This would be x squared plus y squared, plus 2xy in the middle. So these are two different functions that we're talking about. But we can go through the same basic process. We'll let z equal 1, and that means we'll have 1 equals x squared plus y squared. That's our function. And what is that? Well, that's just a circle with radius 1 centered at the origin. All right. What if we had z equal, well, that's right. Let's draw that one first. Here we go. So let's go to here is 1, here's -1, and 1 and 1. So our contour for height 1 would look like this. There we go. And we would label that with a nice 1. And then we go on and try to find something about the shape of the contour at height 2. Well, that would be defined by all the x and y points that satisfy 2 equals x squared plus y squared. What's that, of course? Well, it's a circle with radius equal, careful here, x squared plus y squared equals radius squared. So the radius is actually root 2 in this particular case. And not a big surprise, if we had 3 and 4, we'd have 3 and 4, and we'd have root 3 and root 4 or 2. So we have a nice collection or family of functions again, all circles with different radii corresponding to different heights on the surface. So what would those look like? Well, the last one's probably the easiest to draw. It's a 2. There we go. Maybe not the easiest to draw, certainly the easiest to place on the axes. Anyway, out here at 2, radius 2, and that's at height 4. The other two were at 1.4-ish and 1.7-ish, so there we go. Very much a sketch at this point. That's at height 2. And last but not least, we have the contour at height 3, which is at radius root 3 from the center. Nuts. 2, 3. So again, the z values are in green. So you have to be careful when you're looking at these diagrams and make sure you know which value is being represented by a number being put on the plot. Here we can distinguish with color. Usually it's fairly clear in the context that a number is put in the middle of the line to make it clear that it belongs to the line. It's also worth noting one other point that isn't specifically asked for here. If we look for height 0, we're going to get a single point. And that single point, of course, is at the origin. So a contour doesn't have to be a curve. It can actually be just one point. There it is. The dot in the middle of this diagram is at height 0. There we go. So again, once we have the contour diagram generated by manipulating the function by setting it equal to certain z values and seeing what shapes we get in x and y, oops, forgot to label the axes, x and y, then we ask ourselves, what's the shape here? Notice this has the same quadratic feel, and it takes us one full step to get from 0 to 1 height. then a much smaller step to get from 1 to 2, then smaller still to get from 2 to 3, 3 to 4, smaller still. So we see something that's a surface that's becoming steeper and steeper as we move out from the center. Well, what does this look like? We've actually seen this one before. So here we have the parabolic bowl shape that we introduced as a surface earlier in the last unit. And we've already answered the surface steepness part, and certainly from the diagram we can see that it's a local minimum at the center because the values of z are going down towards the center, and we'd obtain a shape that looks like this if we were to draw it as a surface. But notice this is quite hard to sketch well, whereas this contour diagram is certainly within all your abilities. It's just sketching a graph or multiple graphs in 2 dimensions, and we get the same interpretation by looking at this as we would if we had the surface in 3D. So the contour diagrams are a very rich source of information about the surface of a function of 2 variables, and they're much more accessible than actually drawing surfaces